Yeah, welcome. So the topic we are going to discuss in this lecture is cache coherence. So in the last class we are discussing about SMP, symmetric multiprocessors, and what we have discussed in the sense with symmetric multiprocessors to improve the performance, actually we are introducing cache in each of the multiprocessors. In each of the processors, we are introducing two types of cache, L1 cache and L2 cache. Why we are introducing L1 cache and L2 cache? Because to reduce the access to the bus. If there is no cache, then every time the processor has to fetch the data from the main memory, and for that it has to do that via the system bus, and system bus is a slower device, and hence the processor performance also will become slow, will, will, will get slowed down. Okay, to avoid that we are introducing cache memory. But with the introduction of cache memory, it will lead into a problem. That problem is called as cache coherence problem. So what is cache coherence problem in the sense? Say there is a particular line, say line X, it is available in L1, the cache of this particular processor. Say this line X is available in the cache of this processor also. So the line X is available in both the processors. It is in processor, this processor, and also it is available in this processor. Okay. Now the problem with this is, if this particular processor say updates this particular line, it has updated to X dash. The moment it updates to X dash, then the value of this particular cache for this particular line, it becomes inconsistent or it becomes invalid. So this problem is called as cache coherence problem. Whenever one cache updates, it should immediately reflect back in all other caches. How are we going to ensure that? What are the techniques to follow? That's what we are going to discuss in today's session. Okay, I think the concept is clear. So here I have told just with two caches, but it is not that X should be only in two cache. X can be in any number of caches. It may be in 10 cache or 20 cache or 30 caches. Now even if one of them modified X to X dash, then all the remaining copies will become invalid, or it will be actually it becomes inconsistent. It becomes inconsistent because the respective processors believe that they are consistent, but actually they are not consistent. So this problem is called as cache coherence problem, and how to deal with this problem, that's what we are going to discuss in today's session. Okay, fine. See, before that I want to say a small piece of information. See, if you refer the dictionary, actually coherence means consistency. Actually coherence means consistency. It is not inconsistency. But we say that cache coherence problem. Okay, but in computer science the term may be used in a different way, but you have to understand it properly. Okay, so actually here cache coherence, in the sense we mean the cache creates an inconsistency problem. Okay, so that's what we say, right? Okay, but actually our objective is to make the cache consistent. Okay, from inconsistent we want to make it consistent. So we should not go with the literal meaning of coherence. Actually coherence means consistent, but we say the cache coherence as a problem. So when we say coherence here, actually we mean incoherence or inconsistency. Okay, right? So so let us not go with the English meaning. You have to actually adapt according to the situation. Okay, so here what I'm trying to say in the sense, here cache coherence problem means it is just cache inconsistency problem. Okay, and how we are going to deal with that problem, that's what we are going to discuss. So at the top level, there are two approaches to deal with cache coherence. One is a software based approach, which we call it as software solutions, and the other one is a hardware based approach, or hardware based solutions. Okay, so coming to software based approach, so with software based, how are we going to solve the problem of cache coherence through software? You may get this question. Okay, yeah, it is really tough, but it can be done to certain extent by using through compilers. It can be done certain through to it can be done to through a certain extent by using compilers and through operating system. Okay. So the compilers, when a program is getting executed, the compiler should predict like uh, which of these instructions may create catch coherence problem. The compiler should predict like which of these instructions may create catch coherence problem, and the compiler should ensure that such instructions are not catched. The compiler should ensure that such instructions are not catched. Okay. So the problem of coherence comes when there is a multiple copy of item which is residing in more than one processor, and if one processor updates that item, then the item in all other processors becomes inconsistent. So this is called as catch coherence problem. So the software based approach, what it says in the sense simply, it says that it will, every instruction it will predict like whether this instruction is likely to create a catch coherence problem or not. Like that, every instruction it will predict. If there is a chance that this instruction is likely to create a catch coherence problem, then the compiler or the operating system will not allow this instruction to be catched. It will never be catched. It will be available only in the main memory. So as it is not catched, it won't create a catch coherence problem. Okay. If there is another instruction I2, and if it predicts that it may not create a catch coherence problem, then the compiler will allow this instruction to be catched. Okay. So this is the basic principle by which the software based solution works. The advantage of the software based solution is we need not require any special hardware circuitry or any special logic to deal with catch coherence problem. It can be dealt by the compiler and the operating system itself. Okay. The solution seems to be attractive because there is because the overhead of detecting uh, problems, the overhead of detecting the catch coherence problem is transferred from runtime to compile time. Actually, it's a runtime problem because we don't know when the inconsistency is going to occur. So it is a, what do you call, attractive solution because here the problem is now transferred from runtime to compile time, and the design complexity at the hardware level is shifted to software. Okay. And the design complexity is transferred from hardware to software. Okay. But actually the software based approach, we cannot call it as an efficient approach. It is not a much efficient approach because you cannot always predict what is going to happen, and most often the prediction may not be in a proper way. Okay. So and generally most of these software based approaches, it works based on conservative decisions. Conservative decisions means it makes some assumptions. Based on that, it works. It cannot work dynamically. Okay, because whatever happening, because compile time is compile time, it is not runtime. It is before execution time. So there is no question of any dynamic. You cannot expect any dynamic behavior here. So to be frank, it cannot effectively handle the catch coherence problem. So this is the drawback with the software based approach. Hence we are going for hardware based approach. So these hardware based approaches are generally called as catch coherence protocols. Catch coherence protocol. Okay. So they actually provide solutions at runtime. They actually provide solutions at runtime, and as they provide solutions at runtime, they are more efficient. They are more efficient, and they provide better performance than software based approach. Okay. And also they need not do anything which is really not required at all. Okay. So because only when the problem occurs, this hardware based approach is going to do something. Unless and otherwise there is no problem occurs, it is not going to do anything. But that is not the case with software based approach. Software based approach is just going to predict. It may happen, it may not happen, like that. But whatever it predicts as for a particular instruction, it may predict as it may not be catched, but probably like it may create inconsistency, it may not create inconsistency, like that it may predict one instruction, but that instruction may create uh, inconsistency when it is getting catched. Okay, so all such if the prediction becomes wrong, then we don't know how the software based approach is going to behave. Okay, so in fact hardware based approach actually works better in effectively dealing with the catch coverage problem. Okay, so basically this hardware based approach to deal with catch coverage problem can be classified into two categories. These are directory protocols. One is directory protocols, the other one is Snoopy protocols. Okay, so the entire catch coverage problem can be dealt in two ways. One is software based solution, the other one is a hardware based solution. We are not going to look detail on software based solutions because they are not much efficient techniques. So coming to hardware based solutions, again these hardware based solutions are further classified into two categories. One is called as directory protocols, the other one is called as Snoopy protocols. Okay, so in the context of catch coverage problem, actually the hardware based solutions works much better than the software based solutions. So what is a directory based protocol? So this or you can this directory based protocol is something like it is a centralized approach. There will be a centralized controller, and that centralized controller will decide what should be done when. Okay, so this can also be called as a, it's not another name, just I am saying it is a centralized technique. Whereas this Snoopy protocols, it's a distributed technique. The directory protocol is a centralized approach or technique, and the Snoopy protocol is a distributed technique or approach. Okay. So coming to directory protocols, in a directory protocol there will be a centralized controller along with the bus controller, uh, along with the memory controller. Okay, we have memory controller, right? So along with the memory controller, there will be a centralized controller. Okay, there will be a centralized controller. Say, say for example, this is main memory. Okay, so there is memory controller, right? So apart from memory controller, we have another controller which is called a CC, centralized controller. Okay, centralized controller, or you can consider it as a part of memory controller. Now we have different processors. I am not drawing the processors here, and each of the processors have its own cache. Okay, we are talking about SMP. Okay, so symmetric multiprocessing system. So we may have hundreds of processors, and each of the processor has its own cache. So processor 1 has its cache, processor 2 has its cache, everybody is having its own cache. So we can, if you want, you can number from C1, C2, C3 up to Cn. So all the processor has its own cache. Okay. Apart from this, every processor will have a cache controller. Okay, so every processor will have a cache controller, CC. Whereas this CC is centralized controller. Okay, whereas this CC is cache controller. Every processor will have its own cache controller. Every processor will have its own cache controller. Okay, right? Yeah. So now what happens in the sense? Say for example, if uh, say for example if there is a centralized controller, and that centralized controller is a part of the main memory controller. Okay, and that and directory is nothing but and directory is something which is stored in the main memory. Directory contains global state information about the contents of various caches, various local caches. Okay, so I mean each cache is called as a local cache. So directory is nothing but some space in the main memory. Directory is a space in the main memory which contains information about the state of the local cache. That is, this directory will know exactly what is stored in each cache. Cache 1 contains what? So probably you can assume directory is something like a table. Directory is something like a table which holds information about each and every catch. Like catch 1 contains what type of data it contains, catch 2 contains what, catch 3 contains what. Like that, for all the catches, it will hold the necessary information about each and every catch. Okay, so this is what is about the the directory. Okay, now when an individual catch controller makes a request, the request will first go to the centralized controller. The centralized controller checks, and then it will issue necessary commands for data transfer between main memory and caches, or between caches. Okay, so and also it is the duty of the centralized controller to update uh, the information in the directory. Okay, right. So even for example, if a processor wants to write to a local copy of a cache line, then it must request exclusive access to the line from the controller. If a processor want to modify, okay, if a processor want to modify the contents of its cache, it should request the centralized controller that provide me exclusive access. Okay, then why exclusive access means that I only modify, I want, because if it is going to change, then all others content will become inconsistent. Okay, so it requires an exclusive access. Then the controller will send a message to all the processors. Okay, the controller will send a message to all the processor that we are going to give the exclusive control to one of the processor, right? And and not only that, the processor, the controller will wait for acknowledgement. The controller will wait for acknowledgement from all the processor that exclusive access can be given to so and so processor. When the centralized controller receives the acknowledgement from all the processor, then it will give exclusive right for that particular processor which has request to access the which has requested to modify its cache. Okay, so meanwhile what happened in the sense, all the other cache contents which is holding the same copy, it will be invalidated. Okay, it will be invalidated. The controller sends, so the concept is, see, it is something like this. See, the memory controller is the along with memory controller we have something called as CC, centralized controller. Okay, and in the memory there will be a directory. Directory is nothing but which holds information about the contents of each and every cache. That is, it knows like what data is stored in each cache. Like that, it knows the detail. And each cache will have a cache controller. Each cache will have a cache controller. So the cache, where the cache is present in the processor. So if any processor, if they want to perform a read operation, if they want to read something from the main memory, they cannot directly make a read operation. First, that request will go to CC, centralized controller. The request will go to centralized controller. The centralized controller then it will process the request, and it will allow the processor to read from the main memory, provided if whatever the copy of data this processor is requesting is not in any of the caches. Are you getting? See, if it is asking for a fresh copy of data which is not in any of the cache, then it will allow the processor to access that data from the main memory. Otherwise any one of this cache itself will respond, because this request is coming through the system bus. So processor is requesting that I want this particular data, so I want the data X. But if that data is available in any of the other caches, if that data is available in this cache, then this processor will respond, I have this data, and it will give the data. Okay, this is with respect to read operation in case of directory protocols. In case of write operation, okay, I think it's clear. In case of write operation, if the processor want to modify something in its own cache, say processor contains some data in its cache, processor 1 contains some data here, say there is a data x, this x it wants to modify to x dash, but that also it cannot do directly, because this x we don't know whether this x is only in processor 1 or is it in somewhere else. There may be a copy of x here, there may be a copy of x here, there may be a copy of x somewhere else. So what the processor will do in the sense, again it will place a request to the cache controller, it will place a request to the cache controller. Okay, so what request it will place in the sense, I want exclusive access to x, I want exclusive access to x. Exclusive means what? I should only access x, nobody else should access x. That is what is called as exclusive access. So processor 1 will place a request to the cache controller stating that I want exclusive access to x. Now the cache controller will send a message to all the processor stating that processor 1 want exclusive access to x. So all other processors should invalidate x. Like that it will send a message. Okay, that means whatever the x you are holding, that will be no more valid, because P1 is going to modify it. So you please invalidate and let me know. Like that the centralized controller will give a communication. Now this communication will reach to every processor. So whichever the processor is holding x, they will make x invalid. Okay, they will make x invalid. Invalid means, let us say, how to represent invalid. Say so I am making as IV. So this x becomes invalid. Here also the x becomes invalid. So wherever x is there other than P1, all the other copies of x will become invalid. Okay. After invalidating, they will acknowledge that to the centralized controller, that yes, we have invalidated x. Like that they will acknowledge that to the centralized controller. Okay. Now the centralized controller will grant permission to P1, that what permission? Exclusive permission. Now the centralized controller will give exclusive access for P1 over x. Okay, now P1 will modify x. Now P1 will modify x and x will become x dash. Is it clear? So this is how this directory protocol work. So in directory protocol there will be along with memory controller there will be a centralized controller. Along with every cache there will be a cache controller. For while performing read operation, if any of the processor want to read something from the main memory, the request should come to cache controller. Then the centralized controller. The centralized controller, I mean, why they want to read? The data is not available in its own cache, so that they want to read. So only when there is a cache miss, the processor will request for a read from the memory. But that request will first go to centralized controller. So centralized controller, once it is went to centralized controller, no, during that time other processor also will be watching that request. So if some of them has that particular data or that particular line of cache line of data, whatever the processor is requesting, then they will share that data. Okay, now the processor will get that data. If nobody shares, then the centralized controller will grant access to P1 to get the data from the main memory. This is for read operation. Coming to write operation, if P1 want to update some particular line in its own cache, okay, then also P1 cannot do directly. It should request the centralized controller that I want exclusive control over x, like that it should ask. Because x may be in somewhere else also, because x may be shared with others, so it is not exclusive. So P1 should request for an exclusive access. When any processor requests for an exclusive access, the centralized controller will send a message to all the other processors stating that somebody has asked for an exclusive access for one particular cache line, so that cache line should be invalidated. Like that it will send a message. Now all the processors which is having that particular data, they will invalidate it. After invalidating, they will acknowledge back to the centralized controller. Once the centralized controller receives the acknowledgement, then the centralized controller will give exclusive access to P1 so that P1 can update x to x dash. Okay. So this is how directory based protocol works. So this is the so this particular, this just shows in briefly what is directory based protocol, but whatever we have discussed now, that is the whole concept. Okay, it collects and maintains information about the copies of data in each cache. That is, it maintains a directory in the main memory which contains information about what is stored in each cache. Okay, and this directory is stored in the main memory. Every request or checked against the directory, or you can call it a centralized controller. Okay, centralized controller. Through that, every request will be checked. So through that request, so whenever the request come to the centralized controller, no, through the directory also the centralized controller can understand whether the particular whether if a particular processor is saying that I want this data, then whether it is available with some other processor or not, that can be also checked through the directory. Okay, actually this is an effective technique if it is if the system is a very large and a complex system with if the system is a large, if it's a large scale system with complex interconnection schemes. Okay, complex interconnection schemes in the sense, because all the processors should be interconnected properly. Because when there is a when a processor requests for a data, it is not going to take only from the main memory. Some other processor may also give that. So in that case, all the processors should be properly interconnected. So this protocol will be effective in a large scale system with complex interconnection schemes. Okay, but it may create a bottleneck, because every time all the requests should go to the centralized controller. So that is one type of bottleneck. Okay, and so these are some of the advantage and disadvantage of this particular model. Okay, so this is about directory based protocol, which is a centralized protocol. The next is the Snoopy protocol. The Snoopy protocol is a distributed protocol. Okay, it's a distributed protocol. Here there is no centralized controller. Each cache, each processor will have its own cache controller. Okay, each processor will have its own cache controller, and a cache must recognize when a line that it holds is shared with other caches. So here line in the sense we represent a data. So throughout this it is called as a cache line. Okay, cache line means you can assume one line of instruction. Okay, you can assume cache line as one line of instruction. So if a particular line is shared with other caches or not, that should be known to a given cache. Okay, so a particular cache may contain 10 lines. Okay, out of these 10 lines, how many lines are shared with others, how many lines are not shared with others, that this cache should be knowing. So this is cache C1. Okay, but there you have many caches. Okay, so this line is shared or not, is this is shared or not, is this is shared or not, that should be known to this cache. Okay, if it is shared, let us call it as yes. If it is not shared, then we will call it as E. E means exclusive. Exclusive means only this cache contains this line. Yes means no, it is not exclusive, it is shared with many others also. Okay, so when an updates are performed on a shared cache line, when an updates are performed on a shared cache line, it must be announced to other caches by a broadcast mechanism. Okay, here there is no centralized thing and all. So for example, you can assume something like this. Say there are, let us, for a simple case, let us assume there are 3 caches, cache 1, cache 2 and cache 3. Okay, say in each of the caches there are 3 lines. Say the first line is this is C1, this is cache 1, this is cache 2 in processor 2, this is cache 3 in processor 3, cache 1 is in processor 1. The first line of cache 1, say it is shared. The second line is not shared, which means it is exclusive. The third line is also not shared, it is exclusive. Okay, the first line of cache 2 is shared, second line is also shared, third line is not shared. Okay, the first line of cache 3 is not shared, its second line is shared, its third line is not shared, that is exclusive. Okay, so E represents exclusive, which is not shared, S represents shared. Now assume that this first line of catch 1, it is available in catch 2, it is this one, it is available in catch 3 also. Okay. Now if it is shared, then this catch should know that this is shared. Okay. So now this catch knows that this is shared. But it is shared with whom? All those things it may not be knowing, but it just knows that it is shared. Now this catch is going to update it. It is going to make yes to yes dash. Okay, previously it is yes, now it is making it yes dash. After making yes dash, it will give a broadcast message to everybody, all the processors. Even if there are 100 processors, it will send a broadcast message to all the 100 processors stating that I have changed. The processor 1 will give an update message, broadcast message stating that I have changed yes to yes dash. So if you have a copy of yes, you make it to yes dash. So here there is a copy of yes, it will become yes dash. This yes is different. Okay, so let us assume this is some other yes. Okay, yes not. Okay, so here also there is a copy of yes, it will become yes dash. Okay, so this type of protocol is called as distributed protocol. Here there is no central controller. When updates are performed on a shared catch line, it must be announced to other catches by a broadcast mechanism. Right? So all other catch controllers also should each catch controller is able to snoop on the network to observe these broadcast notification and react accordingly. Snoop means they should keep checking the bus. So how this processor is broadcasting this message through the bus. Okay, so every other processor should frequently snoop on the bus. Is there any information for us? Is there any information for us? Like that they should frequently check, maybe once in every 1 second or something they should check. If there is anything, accordingly they should update. So they should keep on check the bus. That is called a snoop. So it is called a Snoopy protocol. Okay. So each catch controller is able to snoop onto the network or bus to observe these broadcast notification and react or modify accordingly. Okay. Right. So this is also one of the good technique, but the drawback with this technique is, see, if you recall why we are using catch to reduce the bus access. We are using catch to reduce the access to system bus. But again, in Snoopy protocol, we are going to use system bus, because whenever one particular processor is changing the catch, it is going to send a broadcast message through the system bus. So again, we are going to use the system bus. Okay, so we have to take care such a way that increased bus traffic required for broadcasting and snooping does not cancel out the gains from the use of catches. Okay, so this is something like what do you call profit and loss. We are going for catch memory because we want to reduce the system bus access. But now if you use Snoopy protocol, again you have to use system bus access. So you should ensure that we are not going to use system bus to that extent that it will cancel out the gains that were attained by introducing the catches. Okay, so that care must be taken. Okay, right. So this Snoopy protocol is of two types. One is called as write invalidate and the other one is called as write update or write broadcast. Okay, the Snoopy protocol is of two types. One is write invalidate and the other one is write update. Okay, so what is write invalidate and what is write update? That's what we are going to discuss now. So to give a brief, whatever we have discussed so far, so we are discussing about what catch coherence protocol, which is broadly classified into two categories. What are they? Software based solution and hardware based solutions. Again, coming to hardware based solutions, we have two types: the directory based approach, directory protocol, and Snoopy protocol. Again, in Snoopy protocol we have two types: one is write invalidate and the other one is write update. Okay, so what is write invalidate? Write invalidate means, with the write invalidate scheme, there can be multiple readers. Readers in the sense, there can be multiple catch with data, with the same copy of data, and they are only performing read operation on that data. Okay, that is called as readers. So readers means they are a particular copy of data or a particular line can be present in multiple cache, but all these caches are only performing read operation. Okay, so read can be multiple, so that is called as multiple readers, but only one writer at a time is allowed. In a write invalidate approach, there can be multiple readers, but only one writer is allowed at a time. Okay, when a write is required, when a write is required, all other caches of the line are invalidated. Okay, say for example, there are many caches, catch 1, catch 2, catch 3. Okay, say initially all these caches, they are performing read operation on the data X. They are just reading. They want to perform some operation or something. They are not updating, they are just reading X. Okay, they are not changing anything. Okay, say meanwhile one of the processor want to update X. Okay, so how many processors? So multiple readers are allowed, but only one writer is allowed. Only one person can write at a time. So this person, I mean this processor, is now going to make X to X dash. Okay, but before making X to X dash, all these should be invalidated. Okay, all these should be invalidated because that is going to be modified. So this is not valid. No more it is valid. So this processor should, this cache should know that it is invalid. Okay, the same thing only we did in directory control, but there we use what you call, we used a centralized controller, all those things. Here we won't use centralized controller. How it is going to work, that we will be discussing in detail later, but as of now you just understand this much. In a write invalidate approach, there can be multiple readers but only one writer at a time. When a write is required to be done, all other caches of the lines will be invalidated. Okay, right? So before performing the write, everything is invalidated. Okay, this if X is available in any other processors, all the thing will be invalidated. Now whichever the processor want to perform the write operation, it gets what? Exclusive control over X. It gets exclusive control over that particular line. Okay, writing processor then has exclusive access until the line is required by another processor. So now it has exclusive access and it can modify the line. Okay, how long it will have exclusive access? Say it is modifying the line. What do you call? Say it is modifying the line. Okay, so say it is modified. After modifying, say after 2 minutes or 3 minutes, some other processor is asking that now I want X. Okay, now this processor can access X because now it is already modified. Okay, no more write is going on. Now maybe read. So now again both of them can share. Okay, so that's what it means. So the writing processor will get exclusive access to the line until it is required by another processor, until that particular data is required by another processor. Okay, so this write invalidate approach is mostly used in Pentium 4 and PowerPC systems. Okay, and here every line in the cache will be in any one of the 4 states. If the cache contains 100 lines, okay, all these lines, each of the line will be in any one of the 4 states. These are modified, exclusive, shared or invalid. Okay, every line should be marked. Maybe some lines will be in the state modified, some line will be in the state exclusive. Okay, some lines will be in the state shared and some of the lines will be in the state invalid. But each and every line should be in one or other state. There cannot be any line which is not associated with any state. Are you getting? So this write invalidate protocol is otherwise called as MESI protocol, MESI, where M stands for modified, E stands for exclusive, S shared for S means shared, S stands for shared, and I stands for invalid. Okay, so we are going to discuss this MESI protocol in detail, but this is a brief overview. So just understand, in a MESI protocol there can be multiple readers but only one writer at a time. When somebody wants to write to a particular data, then all other copies of the data will get invalidated, and now this processor got the exclusive control and now this processor can perform the write operation. Okay, right. And this type of system and this concept, write invalidate concept, is used in Pentium 4 and PowerPC processors. And in case of write invalidate protocol, every line in the cache will be in any one of the four state. Either it will be modified, exclusive, shared, or invalid. So this protocol is otherwise called as MESI, messy protocol. Okay, fine. The next type of protocol under Snoopy is write update. So in write invalid, we can have multiple readers and one writer, but that is not the case in write update. Write update allows multiple readers and multiple writers. It allows multiple readers and multiple writers. How is that? So how is that in the sense, say for example, there are many caches. Okay, there are many caches, right? Okay. Now if one of the processor want to perform a write operation in a particular line, okay, say line some line it want to perform the write operation, but again in a line is nothing but a collection of word. Some of the word only it is going to modify, right? So in a line it is going to modify few words. Okay, so there are many processors. One of the processor want to perform a write operation on a specific line. Okay, in a line it is going to modify only few words. It is not going to modify all the words, right? Even let it modify all the words also, that's not an issue. But whatever the word it is modifying, say this processor is modifying some particular word in its say this is processor K. Then after modifying, it will send a broadcast message to all the processors stating that in so and so line I have modified so and so word. Okay, so in so and so line, in this particular line, say catch line 10, I have modified this particular word, this sixth word. This information it will communicate to all the processors. So if any other processor is having the same line, maybe in their processor it may be different line, but the content is same, if the content is matching. So if any other processor is having the same line, then they will also modify it. Okay, then they will also modify it. So that concept is called as write update. After performing a write operation, the processor will immediately communicate to all the other processor that I have made this change, you also update, like that. So there can be multiple readers and multiple writers here. When a processor wishes to update a shared line, the word to be updated is distributed to all others, and caches containing the line can update it. Okay. So when a processor wishes to update a shared line, the word that it is going to update, it will distribute to everybody, and it will say that I am going to make this update, so you also update it. Okay. So this is about write update. We are not going to discuss in detail about write update. We are going to discuss in detail about write invalidate, which can also be called as MESI, messy protocol. Okay. So that's what we are going to discuss next, right?